Welcome to Elementary Functions. Today we'll talk about complex numbers and polar coordinates. My name is Wendy Fresh. I'm from Portland Community College and this is Math 112. The objectives for this lesson are to first define a complex number and second, to convert between rectangular and polar forms. We will begin by defining a complex number. Complex numbers are numbers of the form z equals x plus y I, where x and y are real numbers. The real number x is called the real part of the number, and the real number y is called the imaginary part of the number. In addition, I to the second power is defined as -1. Let's look at an example. A complex number z equals x plus yi can be seen geometrically as the point x, y in the xy plane. Label the figure to show that in the complex plane, the horizontal axis is called the real axis, and the vertical axis is called the imaginary axis. So I will call this the real axis, and I will call this one the imaginary axis. So the real axis is my horizontal axis, and the imaginary axis is my vertical axis. Example 2. Draw your own complex plane to plot the following complex numbers. Before I draw that complex plane, let me just identify parts of these complex numbers. In z equals 3 minus 2i, the real portion is the number that doesn't have an I on it, so that would be 3. And the imaginary portion is the part that does have an I on it, so that would be -2. For z equals 2 plus 5i, the real portion is 2, and the imaginary portion is 5. In z equals 3i, the real portion is 0, and the imaginary portion is 3. And in z equals -4, the real portion is -4, and there is no I in this one, and so the imaginary part is 0. To draw my own complex plane, if you recall from the last slide, it doesn't look a whole lot different. The only difference is what I call each one of these axes. The horizontal axis is my real axis. So that's where we're going to see all the real portions of these numbers. And then the vertical axis is my imaginary axis. And that's where we're going to see all the imaginary parts of the number. So for z equals 3 minus 2i, starting at the origin, first of all, actually, let me put some tick marks on here. 1, 2, 3, 4, 5, and -1, 2, 3, 4, and 5. And how about 1, 2, 3, 4, 5 on the imaginary axis, and -1, -2, -3, 4, and -5 on the imaginary axis. All right, so for z equals 3 minus 2i, starting at the origin, the real portion is 3 units, so I'm going to move to the right on the real axis, and then I'm going to go down 2 on the imaginary axis to put me at about right here. That's in my fourth quadrant. Z equals 2 plus 5i. Starting at the origin, I'll move to the right 2, and I'll move up 5. So that keeps me in the first quadrant. For z equals 3i, the real portion is 0, so I'll move nowhere on the real axis, but on the imaginary axis, I'll go up 3. So that puts me right on what we used to call the y-axis. And then for z equals -4, the real portion is -4, so I'll go to the left 4, and the imaginary portion is 0, so I'm just going to be sitting on the real axis. A polar representation of the complex number z equals 3 minus 2i can be written by finding the angle theta and the radius of the circle drawn to the point z equals 3 minus 2i. The radius is called the magnitude, and it's denoted with a z and vertical bars around it. Use what is known about finding angles from an initial side to a terminal side and right triangles and their hypotenuse to find theta and the magnitude of z. Now remember, the magnitude of z is what we know as the radius. So if I connect from the origin to that point 3 minus 2i that was in blue, I believe that I can identify from what we've done before, I can identify a right triangle where the hypotenuse is what I'm trying to find. This seems to have legs that are 3, so I'm going to say 3 squared plus negative 2 squared, and that's going to give me r squared. So I'm using the Pythagorean theorem to find r squared. R is going to be the square root of 13, and so I'm going to say that z is equal to the square root of 13. To find theta, I'm going to use probably my SOHCAHTOA rules. Let me just pull that triangle out and make it a little bit larger. What we have is something that looks like this, and what I know is that I was given that the horizontal length is 3, that the vertical length is negative 2, and that I have a radius of the square root of 13, and I want to find theta. Now the square root of 13 was not given, so I'm going to use the 3 and the negative 2 that were given. My right triangle is in that upper right corner, and so the sides that have been given to me are opposite and adjacent. So I will use tangent and say that the tangent of theta is equal to the side opposite of theta, which is negative 2, divided by the side adjacent. So in my calculator, I'm going to put tangent inverse of negative 2/3. And depending on whether you are in radians or degrees, I am in radians, my answer comes out. I'm going to expect that that answer is either a very large angle, or because I'm moving, it looks like in this little small piece, I'm going to expect a number that's negative. And when I put that in, I get negative 0.588. And just to remind myself, I'm going to go ahead and write radians on this. So let's take a look at converting between rectangular and polar forms. A complex number can be written as z equals x plus yi. A polar coordinate includes r and theta. Now from previous lessons, the relationship between x, y, r, and theta is that x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. So by substitution, we can say the following. If r is greater than or equal to 0, and theta is between 0 and 2 pi, including 0 but not 2 pi, then the complex number z equals x plus yi may be written in polar form as z equals x plus yi equals r times the cosine of theta. So I'm taking what was x and I'm substituting in the r cosine theta, plus r times sine of theta. I'm taking what was y and I'm substituting it in with r sine of theta. Now I do need to put an I on the end, and to make sure that that I is not part of the sine of the angle, I'm going to go ahead and put parentheses around that. Now because both of those terms have an r in it, I can further simplify this by factoring out an r, and that leaves me with r times the cosine of theta plus, I think I'll go ahead and move that I to the front so that I don't have to worry about parentheses, another set of parentheses, times the sine of theta. And that is where the magnitude is equal to the radius. So let's look at an example. This one says to complete the following table, and we are given the rectangular form of a complex number for the first one as z equals 3 minus 2i. Now we saw this one on the previous slide. I did this one intentionally. To rewrite this in the polar form of a complex number, what we have to identify from the x that was given and the y that was given, we have to identify what is the r and what is the theta. Now, what we said on the previous slide was that r is equal to, what did we say? If you go back and look in your notes, you'll see that we said that the r was equal to the square root of 13. And we said that theta was equal to negative 0.588. Now you'll notice that I'm not writing that down, and the reason I'm not writing that down is because if you're going to convert into what we call the polar form of a complex number, there's a requirement on theta. Theta needs to be between 0 and 2 pi. In other words, a negative angle is not going to work. So how do I take that negative angle that was in the fourth quadrant and rewrite it as a positive angle? Well, the answer to that is in finding a coterminal angle. We know that a theta of negative 0.588, if I add 2 pi to that, it's going to take me around the circle and in the same location in that fourth quadrant. So this would equal 5.69, and that's what I'm going to put in the place of theta. Looks like I'm writing too big here. I'm off the chart. For the next one, z equals 2 times the cosine of pi plus I times the sine of pi. Now I'm being given something in polar form. In other words, I'm being given that the r is equal to 2, and I'm being given a theta equal to pi. And what I need to find is the x and the y so that I can write it in rectangular form. Now remember that the relationship between r, theta, x, and y, we listed up above. We said that r times the cosine of theta is equal to x, and we said that y can be found by taking r times the sine of theta. So taking that into practice, let me just do this in red so it separates it out a little bit. I'm going to say that my x value is equal to my r value of 2 times the cosine of pi. Now what is the cosine of pi? Cosine of pi is negative 1, so 2 times negative 1 is equal to negative 2. So I'm going to have z equals negative 2, can you see that negative there, plus what is my y value? My y value will be 2 times the sine of pi, and the sine of pi is 0, and so I get 0 here. So plus 0i. Now whenever you have one of the terms being 0, technically you can leave it in there, but you could also just say, well, 0 times anything, it's going to wipe out. So we could say that this is just z equals negative 2. Now when you have the I term disappear, that's what we say is called purely real. In other words, there is only a real part. There is no imaginary part. Now the other thing I just want to point out to you, we did the arithmetic on how to come up with the x and how to come up with the y. I want you to think about where this point with a radius of 2 and a theta of pi, where that's located. In other words, where is this point? If I just in my mind, or maybe I'll just sketch it out real quick, if I just draw a quick circle, here's my circle. We know that a theta of pi is sitting over here on the left on the x-axis or the real axis. And to have a radius of 2, I would be 2 tick marks out. I'd be 2 tick marks out. Let me just put a point right there. Now, if I think of how to get to that point using a rectangular system, it should be no surprise that I ended up starting at the origin, going to the left 2, and going up 0, because I want to just remain seated on that x or that horizontal axis. So when you end up with an r and a theta that are actually sitting on one of the axes, yes, you can show the algebra in order to get the r and the theta, but you can also do yourself a favor and just plot that point to see where it actually is falling. That might allow you to determine easier what the x and the y are. Now, for the third one, with a theta of 2 pi over 3 and a radius of 2, we are not sitting on an axis. We are sitting somewhere in, I believe, the second quadrant. I think you should pause the video and see if you can come up with what the x and what the y are, given that you have this radius of 2 and you have this theta of 2 pi over 3. Once you've figured it out, go ahead and unpause the video and see if you get the same answer as me. All right, so I'm going to say that x is equal to 2 times the cosine of 2 pi over 3. Now this is where having my unit circle memorized, knowing what the cosine of 2 pi over 3 is helpful. The cosine of 2 pi over 3 is equal to -1/2. And so I get 2 times -1/2, which is -1. And for my y value, I get 2 times the sine of 2 pi over 3. Again, if you plug sine of 2 pi over 3 into your calculator, you may get a decimal approximation. It is always preferred to write an exact answer. So what is the exact measurement of sine of 2 pi over 3? Well, if you have it memorized, you know that the sine of 2 pi over 3 is equal to the square root of 3 over 2. Now look how nice this turns out. The 2 in the numerator and the 2 in the denominator cancel out, and so I'm left with the square root of 3. So that tells me that the rectangular form of the polar number, 2 times the cosine of 2 pi over 3 plus I times the sine of 2 pi over 3 is equal to z equals -1 plus the square root of 3i. Now, if you think about this for just a second, the point that involves an x value of -1, an x value of -1, and a y value of square root of 3 is in the second quadrant, which matches with me having an angle measure of 2 pi over 3. That would also be in the second quadrant. So you've got to make sure that those match. Now, in the 18th century, Swiss mathematician Leonhard Euler made a connection between exponential functions and the sine and cosine functions involving complex numbers. He came up with what is now deemed as Euler's formula that says e raised to the I theta is equal to the cosine of theta plus I times the sine of theta. Now, that cosine of theta plus I times the sine of theta should look familiar. We just worked with some stuff like that. Also, notice that Euler's formula deals with the number e, and I say the number e because you might remember from previous math classes that e is approximately 2.7, so it is just a number. Now, using Euler's formula, and we're not having to derive Euler's formula, but using Euler's formula allows us to take the definition from the previous page and write it to show the progression of a complex number in a rectangular form, and rewrite it in polar form, and then also polar form using Euler's formula. Here's how that will look. So we start out with z equals x plus yi, and like we said, this is what we call rectangular form. Rectangular form. And then we saw in the previous slides that we let the value of x be replaced with r cosine theta, and we let y be replaced with r sine of theta. Then, because both of those terms had an r, we factored the r out, and we're left with cosine theta plus I sine of theta. We called this the polar form. And we call this the polar form because all of a sudden now we have r's and thetas. Some books will also call this the trig form because of the fact that you have cosine and sine. We're going to call this the polar form. And then on the next line, you'll see that we still have that r pulled out, but now in the place of the cosine theta plus I sine of theta, we are going to go ahead and substitute in Euler's formula. That gives us, again, what we call the polar form, but you may even want to say polar form using Euler. Okay, so the one above it, you might say polar form using trig. And when I say trig, I mean sine and cosine, and when I say Euler, I mean using Euler's formula that involves E. So now let's take a look at an example. We're going to use Euler's formula to extend the table that we saw in example 3. In example 3, we had z equals 3 minus 2i, and we said that the polar form of that was z equals, and we said that the r value was the square root of 13, and we said that the cosine of the angle would be 5.69 approximately. It's not a perfect number, so we're going to go ahead and round that to 2 decimal places, and then of course put the 5.69 here as well. Now in polar form using Euler's formula, it's not that bad. The radius we've already found, and the E and the I are going to stay, and we're simply going to put that 5.69 in as our theta. Now I left some room underneath here because I want to come back to this one in just a minute and maybe just adapt a couple of things and show you how you would deal with them. Let's go on to the second one though. We have z equals 2 times the cosine of pi plus I times the sine of pi. We said that that was equal to z equals negative 2, and of course we called that purely real. Using Euler's formula, we would say that this is equal to z equals 2e to the I pi power. Now I can call it I pi or I can call it pi I. It doesn't make a difference because multiplication is commutative, so you do whichever feels easiest for you to write. For the third one, we found that we were in the second quadrant. We found our x value as negative 1, and we found our y value as the square root of 3. Again, all of the computations here are from example 3. Writing this using Euler's formula, simply going to substitute the 2 in for the r, and I'm going to have e raised to the 2 pi over 3i. All right, so no computations so far. The last one is now we're being given the polar form of a complex number using Euler's formula. So the 3 is being given to us as r, and the pi over 2 is being given to us as theta. So I'm just going to go ahead and substitute that in for the polar form of a complex number using sine and cosine. This is going to give me z equals 3 times the cosine of pi over 2 plus I times the sine of pi over 2. There it is. Now, you may or may not have noticed this, but if I'm going to the rectangular form, of course, we know that to find x, that's equal to r cosine theta. You might just think of it like this. We know that this is r, and we know that this is the cosine of theta. So if I just imagine in my head that I am actually distributing that, that's going to give me this x value. What is 3 times the cosine of pi over 2? Well, the cosine of pi over 2 is 0, so 3 times 0 is 0. Plus, now I'm going to distribute the 3 to the sine of pi over 2. The sine of pi over 2 is 1, and 3 times 1 is 3, so 3i. Now, just like you saw me do on the second line where I said it was purely real, and I crossed out the imaginary term, I can also cross out this real term and just say that this is 3i. So this one would be considered purely imaginary. And there it is. Hopefully you also take my advice and think about where would a point land on a circle that was sitting at a theta of pi over 2 with a radius of 3. And I think if you think about that and then you think about how would you get to that point, this answer of having x as 0 and y as 3 makes sense. Now, I want to go back to the very first one and I want to just show you something. If I changed this one to z equals negative 3 plus 2i, I want you to think about this for a second. What would the radius be? Well, the radius, I believe, would still be the square root of 13. And that is because the radius is coming from, and I'm just going to go ahead and write up above in this green line here, the radius, of course, is coming from x squared plus y squared, and my x is negative 3 squared, and my y is 2 squared. And I believe that that's going to get me the same result as if I had the positive 3 that I originally had and negative 2, which I originally had. Squaring is going to turn both of those positive, and so that's why I still get the square root of 13. So you might be thinking to yourself, okay, well, how is it possible that she just changed the numbers and we still have the same radius? Well, think about this for a second. The original problem, 3 minus 2i, that one was in quadrant 4, and negative 3 plus 2i is in quadrant 2. So the radius hasn't changed, but the quadrant has. So what that tells me is that I'm going to expect a different angle measure on this one. In other words, 5.69 for sure got me into the fourth quadrant. 5.69 will not get me into the second quadrant. So what do I need to do? Well, let me show you. We're going to say that tangent of theta is equal to my y value, which is 2, over my x value, which is negative 3. Now theta is going to be equal to tangent inverse of negative 2/3. Now I hope it's not a surprise that when you put that into your calculator, you still get that same negative angle measure that you got with the original one. And that's because your calculator doesn't see a difference between taking 2 and dividing it by negative 3 versus negative 2 and dividing it by positive 3. Your calculator is just going to treat that as negative 2/3. And so when you put that into your calculator before, you got negative 0.588. Now negative 0.588 is in the fourth quadrant. So all I had to do on the first one was add 2 pi to it. That got me into that same fourth quadrant. But how do I get a second quadrant answer? Well, this is where remembering the period of the tangent function helps. Remember, we've talked about this a lot. When you plug an inverse into your calculator, the calculator is only giving you one possible answer, but there's a lot more. In fact, if I add pi to this, because pi is the period of the tangent function, I will get another possible answer. Negative 0.588 plus pi is equal to what? Go ahead and put that into your calculator. When I do that, I get 2.55. I think that's what I got. And 2.55 is in the second quadrant, and so that tells me that that will work. And so I'm going to just transfer all this over and get my answer for your Euler's formula. So I guess the moral of the story here is that you need to use the math that you know in order to find r and theta. But when it comes to finding theta, it's really important to pay attention to what quadrant is my original point in, and making sure that the theta that you get matches that quadrant. And if it doesn't, then you're going to make use of either adding the period of the function or adding 2 pi in order to stay in that quadrant, but just write it in a different form.